I've been thinking a lot about the multiverse lately, and it's one of those ideas that seems almost too wild to be true, too science fiction to be actual science. But here's the thing that keeps me up at night, the thing that makes this so fascinating and so deeply unsettling at the same time. Some of the most brilliant physicists and cosmologists alive today take this idea seriously, really seriously, not as a fun thought experiment or a plot device for movies, but as a genuine possibility that might actually describe the reality we live in. And when you start to dig into why they think this, when you really look at the evidence and the reasoning behind it, well, you start to realize that the universe might be far stranger, far more vast, far more incomprehensible than anything we ever imagined. So what is the multiverse? At its most basic level, it's the idea that our universe, everything we can see and measure and detect, all the galaxies and stars and planets stretching out for billions of light years in every direction, that all of this might be just one universe among many, maybe among infinitely many. And these other universes, these parallel realities, they might be completely separate from ours, existing in some sense alongside our universe, but forever beyond our reach, forever undetectable, forever isolated. In some of these universes, the laws of physics might be different. The constants of nature might have different values. The whole structure of reality might be fundamentally unlike anything we know. And in others, maybe in infinitely many others, things might be almost exactly like they are here, with just tiny differences, small variations that branch off from our reality in ways both profound and trivial. Now, I know what you're thinking. This sounds crazy, right? It sounds like something someone made up because they watched too many science fiction movies or read too many comic books. And I get that reaction, I really do, because when I first encountered this idea, that's sort of what I thought too. But here's what changed my mind, or at least made me take it seriously. This isn't an idea that scientists came up with because they wanted the universe to be more interesting or more dramatic. It's an idea that emerged almost reluctantly from the actual mathematics and physics of our best theories about how reality works. Nobody set out to discover the multiverse. It found them. It appeared unbidden and unwanted by many as a consequence of taking seriously the equations that describe quantum mechanics or cosmic inflation or string theory. And that's what makes it so compelling and so troubling at the same time. Let me back up a bit, because to really understand how we got here, how we arrived at this bizarre conclusion that there might be infinite versions of reality, we need to start with something more familiar, something closer to everyday experience. Think about a choice you made today. Maybe it was something small, like whether to have coffee or tea, or something bigger, like a conversation you decided to have or avoid. When you made that choice, it felt like you were selecting one path from several possibilities, right? You chose coffee, but you could have chosen tea. You said yes, but you could have said no. And after you made that choice, the other possibilities, they just sort of disappeared. They became roads not taken, alternate paths that exist only in your imagination, in your sense of what might have been. But what if they didn't disappear? What if in some real sense all those other possibilities actually happened? Not in your imagination, not as mere hypotheticals, but as genuine realities that exist somewhere somehow, just as real as the reality you're experiencing right now. That's the essence of one version of the multiverse idea, and it comes from quantum mechanics, the theory that describes how the smallest constituents of matter and energy behave. And quantum mechanics, well, it's the most successful scientific theory we've ever developed in terms of making predictions that match experimental results. It's been tested countless times in countless ways, and it works. It works so well that virtually all modern technology, from computers to smartphones to medical imaging devices, depends on it being correct. But there's a problem with quantum mechanics, a deep conceptual problem that's bothered physicists since the theory was first developed nearly a century ago. And the multiverse, or at least one version of it, emerges as a possible solution to that problem. You see, quantum mechanics tells us that particles don't have definite properties until they're measured. Before you look at an electron, before you measure its position or its momentum, it exists in what's called a superposition, a kind of fuzzy, indefinite state where it's in multiple states at once. The electron isn't here or there, it's sort of both, or neither, or something else entirely that we don't really have words for because it's so unlike anything in our everyday experience. And this isn't just a matter of us not knowing where the electron is. It's not that the electron is really in one specific place and we just don't know which place that is. No. According to the mathematics of quantum mechanics, the electron genuinely doesn't have a definite position until someone or something measures it. It exists in this superposition of possibilities, and only when a measurement happens does it collapse into one definite state. But here's the deeply weird thing, the thing that drove physicists mad for decades and still drives many of them mad today. What counts as a measurement? What causes this collapse from many possibilities to one definite reality? When you look at the electron, does your observation, your consciousness, your awareness cause the collapse? Or does any interaction with any other particle count as a measurement? And if any interaction counts, then when does the collapse actually happen and why? The standard interpretation of quantum mechanics, developed by Niels Bohr and his colleagues in Copenhagen in the 1920s and 1930s, basically said, well, we don't really know, and maybe we shouldn't worry about it too much. The theory works, the predictions match experiments, so let's just use it and not ask too many questions about what's really happening. And for a long time, that's what most physicists did. They learned to shut up and calculate, as the physicist David Mermin once put it, using quantum mechanics as a tool without worrying too much about what it meant. But not everyone was satisfied with that approach. Some physicists, some thinkers, they couldn't let it go. They wanted to know what was really happening, what the mathematics was actually describing. And in 1957, a young physicist named Hugh Everett, working on his doctoral thesis at Princeton, proposed a radical solution. What if, he asked, there is no collapse? What if all the possibilities, all those states in the superposition, they all actually happen? Not in some vague, hypothetical sense, but really happen in separate branching universes. When you measure that electron and find it here, in some other universe, another version of you finds it there. Both outcomes are real, both versions of you are real, and both universes are equally real. They've just split off from each other, diverged into separate branches of reality that can never interact again. This is the many worlds interpretation of quantum mechanics, and when Everett first proposed it, most physicists thought it was insane. The idea that the universe splits every time a quantum measurement occurs, creating countless trillions upon trillions of new universes every second, each one as real as our own, it seemed absurd, extravagant, impossible to take seriously. But Everett argued that this interpretation was actually more economical than the Copenhagen interpretation, more elegant, because it didn't require this mysterious, undefined process of collapse. It just took the mathematics of quantum mechanics seriously, following the equations wherever they led. And where they led was to a multiverse of staggering proportions, a reality so vast that every possible outcome of every quantum event actually occurs somewhere. Now, I need to pause here for a moment because this is hard to wrap your mind around, isn't it? The idea that every time a quantum particle could do one thing or another, reality splits into separate branches where both things happen. It's almost too much to conceive. Think about what that means. Every quantum event, every interaction between particles, every moment of fundamental uncertainty at the quantum level, all of these create new branches, new universes. And quantum events are happening everywhere, all the time, in every atom, in every particle, in every fraction of a second. The branching is constant, unceasing, infinite. From the moment of the Big Bang to now, the universe has been splitting and splitting and splitting, creating an incomprehensibly vast tree of parallel realities, all of them real, all of them evolving according to the same laws of physics, but each one following a different path through the landscape of possibilities. And here's where it gets even stranger, because if the many worlds interpretation is correct, then there are versions of you in some of these other universes. Not just vaguely similar people, but actual alternate versions of you, people who share your history up to some point where a quantum event went differently. Maybe there's a universe where you chose tea instead of coffee this morning. Maybe there's one where you never met your best friend because some random quantum fluctuation caused atoms to move differently in some crucial moment. Maybe there's one where you made a different career choice or lived in a different city or never existed at all because some quantum event in your parents' past went differently. All of these possibilities, if many worlds is correct, are actual realities playing out in parallel universes. But wait, you might be thinking this is just one interpretation of quantum mechanics, right? Just one way of understanding the mathematics. And that's true. There are other interpretations, other ways of making sense of quantum mechanics without invoking countless parallel universes. The Copenhagen interpretation, the pilot wave theory, the objective collapse theories, there are alternatives. But here's the thing, none of them are completely satisfying either. They all have their own problems, their own weird features that seem hard to accept. And many worlds, despite seeming extravagant with its infinity of universes, has gained more and more respect among physicists over the decades. It's still controversial, still debated, but it's no longer seen as fringe or crazy. Serious physicists take it seriously, and some surveys suggest it might even be the most popular interpretation among quantum physicists today. That doesn't mean it's right, but it means we can't dismiss it out of hand. And many worlds is just one source of the multiverse idea. There's another completely different line of reasoning that leads to the same conclusion, and this one comes from cosmology, from our understanding of the very early universe and how it expanded and evolved. This is called the inflationary multiverse, and it's based on a theory called cosmic inflation that was developed in the 1980s by physicists like Alan Guth and Andre Linde. Inflation was invented to solve some puzzles about the Big Bang, some features of our universe that were hard to explain with the standard Big Bang model. Why is the universe so uniform, so similar in every direction we look? Why is it so flat, so close to the critical density between expanding forever and collapsing back in on itself? These seemed like incredible coincidences, fine-tuned initial conditions that begged for an explanation. Inflation provided that explanation. The idea is that in the very first fraction of a second after the Big Bang, the universe underwent a period of exponentially fast expansion, growing faster than the speed of light, ballooning from something smaller than an atom to something much larger than what we can see today, all in something like 10 to the minus 32 seconds. I know that sounds impossible, expanding faster than light, but it's actually allowed by Einstein's general relativity because it's not matter or energy moving through space faster than light. It's space itself expanding, stretching, carrying everything along with it. And this rapid expansion, this inflation, would have smoothed out any irregularities, flattened any curvature, and explained those puzzling features of our universe that seemed so finely tuned. But here's where it gets interesting for the multiverse. When physicists worked out the details of inflation, they realized something remarkable and somewhat troubling. Once inflation starts, it's really hard to stop it everywhere at once. In most versions of inflation theory, the process is driven by a field called the inflaton field that permeates space. And this field can decay, dropping to a lower energy state and ending inflation. But quantum fluctuations mean it doesn't decay everywhere at the same time. In some regions, inflation stops and a universe like ours forms. But in other regions, it keeps going, continuing to inflate. And within those regions, there can be yet more regions where it stops, creating more universes, and so on forever. It's like a fractal, an eternal process of bubble universes forming within an ever-inflating cosmic foam. So eternal inflation, as this is called, naturally produces a multiverse, not a multiverse of quantum branching like many worlds, but a multiverse of separate bubble universes, each one potentially huge, each one potentially with different properties. And the thing is, we might be living in just one bubble, one pocket universe within this vast inflating structure, and all the other bubbles would be forever beyond our reach, because the space between them is inflating faster than light. We couldn't travel to them, couldn't see them, couldn't communicate with them in any way. They would be as isolated from us as if they existed in some entirely separate reality, which in a sense they do. And those other bubble universes, they might not be exactly like ours. In fact, if certain theories are correct, they're probably quite different. This is where string theory enters the picture, adding yet another layer to the multiverse concept. String theory, as you might know, is an attempt to unify quantum mechanics and general relativity to create a single framework that describes all the fundamental forces and particles. It proposes that the basic constituents of reality aren't point-like particles, but tiny vibrating strings of energy, and the different vibrations correspond to different particles and forces. It's an elegant idea in many ways, but it comes with some baggage, some features that many physicists initially found uncomfortable. One of those features is extra dimensions. String theory requires more than the 3 dimensions of space and 1 dimension of time that we experience. Depending on the version, it needs 9 or 10 spatial dimensions for the mathematics to work. Now, we obviously don't see these extra dimensions, so where are they? The answer string theorists came up with is that they're curled up, compactified into tiny shapes so small we can't perceive them, like how a garden hose looks like a 1 dimensional line from far away, but up close you can see it has a circular dimension wrapped around its length. These extra dimensions are curled up at every point in space, but they're so tiny, so far below anything we can measure, that we don't notice them. But here's the crucial thing. There are many, many different ways these extra dimensions could be curled up. Imagine a piece of paper that you can roll or fold in countless different configurations. Similarly, the extra dimensions of string theory can be compactified in an enormous number of different ways, and each different configuration, each different shape of the extra dimensions would give rise to different physics. The particles and forces, the constants of nature, even the number of dimensions we perceive, all of these could vary depending on how the extra dimensions are arranged. String theorists call this the landscape, and it's not a small space. Current estimates suggest there might be something like 10 to the 500 different possible configurations, maybe more. That's a number so large it's almost meaningless, far more than the number of atoms in the observable universe, far more than anything we can really comprehend. And if eternal inflation is real, and if string theory is correct, then each bubble universe in the inflationary multiverse might have a different configuration of extra dimensions, a different point in the string landscape, and therefore different physical laws. Some universes might have stronger or weaker gravity, some might have more or fewer types of particles, some might have physics so different from ours that atoms couldn't form, or stars couldn't ignite, or life as we know it could never emerge. The vast majority of possible universes would probably be sterile, lifeless, incapable of supporting anything like the complex structures we see around us. But in an infinite multiverse, or even just an unimaginably large one, even unlikely things happen somewhere. And we, of course, can only exist in a universe capable of supporting life. So it's not surprising we find ourselves in one of the rare special bubbles where the physics happens to be just right. This is called the anthropic principle, and it's one of the most controversial aspects of multiverse theory. The idea is that we shouldn't be surprised to find ourselves in a universe with the right properties for life, because if the universe didn't have those properties, we wouldn't be here to observe it. It's like a lottery winner asking, "Why did I win?" Well, someone had to win, and you're only asking the question because you're the winner. If you hadn't won, you wouldn't be asking. Similarly, in a multiverse with vastly different physical laws in different regions, conscious observers like us can only exist in the tiny fraction of universes where conditions permit life. So we're guaranteed to find ourselves in one of those special places, even if they're incredibly rare, because we couldn't exist anywhere else. Some scientists find this deeply satisfying, a resolution to what had seemed like impossible coincidences in our universe. Why is gravity so weak compared to the other forces? Why is the cosmological constant so small? Why do the fundamental constants have the values they do? For decades, these seemed like mysteries, fine-tuning problems that suggested either incredible luck or some kind of design. But the anthropic principle in a multiverse offers a different answer. These constants aren't fine-tuned for life. They're randomly different in different universes, and we happen to live in one where they permit our existence because we couldn't live anywhere else. It's not that the universe was made for us, it's that we can only exist in universes compatible with our existence. But other scientists hate this idea, absolutely hate it. They argue that it's giving up on science, abandoning the search for deeper explanations. Instead of asking why the constants have the values they do and looking for some underlying principle or mechanism, the anthropic reasoning just says, well, they're different everywhere, and we're here because we can be here. That's not an explanation, critics say, that's just accepting the mystery and stopping the inquiry. And worse, it's unfalsifiable. If every possible universe exists somewhere in the multiverse, then any observation we make can be explained by saying, well, that's just how it is in our particular universe. You can't make predictions, can't rule anything out, can't test the theory in any meaningful way. It becomes, in the words of some critics, not science but philosophy or even religion, a belief system that can accommodate any evidence because it forbids nothing. This question of testability is really at the heart of the multiverse debate, and it's worth spending some time on because it gets at fundamental questions about what science is and what kinds of theories we should take seriously. Traditionally, a scientific theory is supposed to make predictions that can be tested. You propose a mechanism or a model, you derive what it implies for observations, and then you go out and check whether those implications match reality. If they don't, the theory is wrong, or at least incomplete, and you need to modify it or replace it. If they do match, the theory gains support, though it's never proven absolutely true because future observations might contradict it. This process of prediction and testing is what separates science from other ways of thinking about the world. But the multiverse seems to violate this principle because, by definition, the other universes are unobservable. We can't travel to them, can't see them, can't detect them in any direct way. So how can we test whether they exist? How can we falsify the theory? If we can't, then is it really science at all? These are the questions that multiverse skeptics raise, and they're not easy to dismiss. The physicist Paul Steinhardt, for instance, who helped develop inflation theory, has become one of its harshest critics precisely because of these issues. He argues that eternal inflation, by predicting everything and nothing, by generating an infinite multiverse where every possibility occurs, has ceased to be a scientific theory and become an unfalsifiable metaphysical framework. But proponents of the multiverse have responses to these objections. They point out that we don't directly observe lots of things we consider scientifically real. We don't directly observe quarks or black hole interiors or the far side of the cosmological horizon, but we infer their existence from indirect effects. Maybe the multiverse is similar. Even if we can't see other universes, we might be able to see their effects on our universe, or we might be able to test the theories that predict the multiverse as a consequence. If inflation is correct and we find evidence for inflation, and if inflation necessarily leads to eternal inflation and a multiverse, then we've indirectly confirmed the multiverse even though we can't observe other universes directly. And there are some proposals for how we might find evidence. For instance, if another bubble universe collided with ours in the distant past, it might have left a mark on the cosmic microwave background, the afterglow of the Big Bang that we can still detect today. We could look for unusual patterns, cold spots, or other anomalies that might be signatures of such a collision. Or we might be able to make statistical predictions about what kinds of physical constants are more likely in a multiverse with certain properties, and check whether our constants match those predictions. These approaches are controversial, and the evidence so far is ambiguous at best, but they show that the multiverse isn't necessarily completely untestable. There's also a philosophical argument that the question of testability is more subtle than it first appears. What we test in science isn't always the final conclusion, but the reasoning that leads to it. If a well-tested theory, a theory with lots of empirical support, has the multiverse as a logical consequence, then rejecting the multiverse means rejecting the theory, or at least part of it, even though the theory works well in all the domains where we can test it. It's like, imagine a theory that correctly predicts everything we can observe, but also predicts something beyond observation. Do we reject the whole theory because of that untestable prediction, or do we accept the untestable part because the testable parts work so well? It's not clear that there's a simple answer. And this brings us to a deeper point about the multiverse debate, which is that it's not just about physics or cosmology, but about the philosophy of science itself, about what kinds of theories we should accept and what counts as evidence. Some physicists, particularly those influenced by Karl Popper's philosophy of science, insist that falsifiability is essential, that any theory that can't be proven wrong isn't scientific. Others, influenced by different philosophical traditions, argue that we should accept theories that provide the best explanations, that make sense of the most observations, even if they have untestable elements. Science, they say, has always involved some degree of inference beyond direct observation, some leap from the seen to the unseen. And honestly, I think this is where the multiverse discussion becomes most interesting, because it forces us to confront questions we usually don't have to think about. Most of the time, science proceeds without worrying too much about philosophy. We observe, we theorize, we test, we refine, and it all works out reasonably well. But every so often, we hit a boundary case, a situation where the normal methods and assumptions break down or at least become questionable, and we have to think more carefully about what we're doing and why. The multiverse is one of those boundary cases. It challenges our intuitions about reality, about existence, about what it means for something to be real if we can never observe it. And different scientists, different thinkers, they come down on different sides of these questions based on their philosophical priors, their intuitions about how science should work. Let me try to give you a sense of just how many different multiverse concepts there are, because so far I've mainly talked about two, the many worlds quantum multiverse and the inflationary bubble multiverse. But there are others, and they're all quite different in their specifics, even though they all involve the idea of multiple realities. The physicist Max Tegmark proposed a taxonomy of multiverses, a classification system with 4 levels, each more expansive and more philosophically radical than the last. And understanding these levels can help us see the full scope of what people mean when they talk about the multiverse. Level 1 is the simplest, and it doesn't even require any exotic physics. It's just the consequence of infinity. If space goes on forever, which many cosmologists think it might, then eventually everything that can happen will happen somewhere, just by chance. Think about it this way. There are only finitely many ways to arrange atoms in any given volume of space. The number is huge, incomprehensibly vast, but it's finite. So, if space is infinite, then somewhere, far beyond our cosmic horizon, far beyond what we can ever see, there must be regions of space with the exact same arrangement of atoms as here. There must be another Earth, another you, living a life identical to yours up to this very moment. And not just one, infinitely many, because in an infinite space, every possible configuration occurs infinitely many times. This is the level 1 multiverse. And it's not really multiple universes in the sense of separate realities, it's just different regions of one infinite universe. But they're so far away, separated by such vast distances that light will never have time to travel between them, that they might as well be separate universes. Level 2 is the inflationary multiverse I talked about earlier, where different bubble universes with potentially different physical laws exist within the eternally inflating structure. This is more radical than level 1 because now we're not just talking about different regions with different arrangements of the same stuff. We're talking about fundamentally different physics, different constants, different particles, different forces. The level 2 multiverse is not just big, it's diverse in a much deeper sense. Level 3 is the many worlds quantum multiverse, where every quantum possibility branches into its own reality. This is different from level 1 and 2 because it's not about different regions of space or different bubble universes. It's about the fundamental structure of quantum reality itself, about what happens at every moment in time as quantum possibilities actualize. Interestingly, Tegmark argues that level 3 doesn't really add anything beyond level 1 and 2 in terms of the diversity of outcomes. If infinite space and eternal inflation already generate all possible arrangements and all possible physical laws, then quantum branching doesn't create any new possibilities. It just creates them in a different way through a different mechanism. But whether that's true is debatable, and many physicists see many worlds as a distinct type of multiverse. And then there's level 4, which is the most abstract and most philosophically radical of all. This is what Tegmark calls the mathematical universe hypothesis, the idea that every mathematically consistent structure exists as a physical reality. Not just the universes with different laws derived from string theory, not just the quantum branches, but every possible mathematical structure, every possible set of equations that could describe a reality. If you can write down a consistent set of rules, a mathematical framework that doesn't contradict itself, then somewhere, in some sense, that structure is real and embodies a physical universe. This is almost impossible to wrap your mind around because it means there are universes with 3 spatial dimensions, 4 spatial dimensions, 17 spatial dimensions, universes where time flows differently or doesn't exist at all, universes with physics so alien we couldn't even begin to conceptualize them. Anything that can be mathematically defined exists. Now, level 4 is really out there, and even among multiverse enthusiasts, many find it too speculative, too far removed from anything we could ever test or verify. But Tegmark argues that it's actually the logical endpoint of certain assumptions about mathematics and physics. If you believe that mathematics describes reality, and if you believe that mathematical existence is the same as physical existence, then why should only one mathematical structure be real? What would select it? Why this particular set of equations and not others? The most democratic answer, in some sense, is that they're all real, all equally existent. But whether that's profound or just nonsense is something people disagree about pretty strongly. What I find fascinating about Tegmark's taxonomy is how it shows the progression from the almost mundane, just different regions of space, to the utterly bizarre, all possible mathematical structures as physical realities. And each level emerges from taking seriously some aspect of our theories or some philosophical principle. Level 1 from infinity, level 2 from inflation and string theory, level 3 from quantum mechanics, level 4 from mathematical Platonism. None of them were invented just for fun. They all have some grounding in physics or philosophy, but each one also requires accepting something that seems extravagant or counterintuitive. And that raises a question that I think is really central to the whole multiverse debate. What's more extravagant, accepting the multiverse or accepting the alternatives? Is it more reasonable to believe in countless parallel realities, or to believe that our universe is just incredibly, impossibly lucky, that the constants happen to have the right values for life by sheer chance, one in a trillion coincidence? Or that there's some unknown mechanism that selected these particular values for reasons we don't understand and maybe never will? Every option seems problematic in some way, and the choice between them depends partly on empirical evidence, partly on theoretical considerations, but also partly on temperament, on which kinds of mysteries and which kinds of extravagance you find more acceptable. Some scientists argue that we should follow Occam's razor, the principle that simpler explanations are preferable to more complex ones. But what counts as simpler? The multiverse posits an enormous number of unobservable entities, other universes, which seems very complex. But the actual theory that generates the multiverse, like inflation or many worlds, might be simpler than alternatives. Many worlds, for instance, is just the Schrödinger equation, the basic equation of quantum mechanics, without adding any extra mechanism for collapse. Inflation is a straightforward extension of general relativity with a specific type of field. In terms of the underlying theory, these are actually quite simple and elegant. It's only their consequences, the infinity of universes, that seem complicated. So which do we count? The simplicity of the mechanism or the complexity of the outcome? There's no obvious answer, and different people make different calls. Let me shift gears a bit and talk about what the multiverse means, what it implies for how we think about ourselves and our place in reality. Because I think this is where the idea becomes not just intellectually interesting, but personally meaningful or troubling, depending on your perspective. If the multiverse is real, then you're not alone. I don't mean that in the sense that there are other people in this universe, though obviously there are. I mean, you're not alone in the sense that there are other versions of you in other universes living other lives. And this raises some profound questions about identity and meaning. Who are you, really? Are you just this particular version, this particular sequence of experiences in this particular universe? Or are you somehow the collection of all your versions across all the branches, all the possibilities? If you make a decision and many worlds is true, then there's a universe where you made the opposite decision. Both versions exist. Both are real. Both are you in some sense. Does that diminish the importance of the choice? If every possibility actualizes somewhere, then in some sense you didn't really choose at all. You did everything, tried everything, experienced everything across the multiverse as a whole. Or does it not matter because each individual version only experiences their own branch? And for that version, the choice was real and meaningful. Philosophers call this the problem of personal identity in a multiverse, and it's not clear how to think about it. Traditional notions of selfhood, of being a single unified person with a single life story, they seem to break down or at least become more complicated when you consider that there might be countless versions of you, all equally real, all with equal claim to being you. Are they all you? Are you all of them? Or are they separate people who happen to share a common origin? And if they're separate, at what point did they become separate? with every quantum branching event, no matter how small. That would mean you're splitting into separate people, trillions upon trillions of times every second, which is a bizarre thought. And what about consciousness? This is where things get really murky, because we don't understand consciousness well enough to know how it relates to quantum mechanics or the multiverse. Some people, like the physicist Roger Penrose, have speculated that consciousness might be connected to quantum processes in the brain, and if that's true, then maybe there's some interaction between consciousness and quantum branching. Maybe your conscious experience, your subjective sense of which branch you're on, is itself part of the quantum measurement process. But this is highly speculative, and most neuroscientists don't think consciousness requires quantum mechanics at all. They think it can be explained through classical neural processes. So maybe consciousness just goes along for the ride, experiencing one branch or another without playing any special role in determining which one. There's also the question of probability in many worlds. If all outcomes happen, then why do we experience probabilities? Why do some quantum outcomes seem more likely than others? In a multiverse where everything happens, what does probability even mean? This is called the measure problem, and it's one of the technical challenges for many worlds. The answer that some people give is that probability in many worlds is about the weight or amplitude of different branches. The mathematics of quantum mechanics assigns different amplitudes to different outcomes, and these amplitudes square to give the probabilities we observe. So, in many worlds, every outcome occurs, but some occur in branches with higher amplitude, and maybe your subjective experience is more likely to find itself in high amplitude branches, though exactly why is not entirely clear. It's an active area of research and debate. The existential implications of the multiverse extend beyond personal identity to questions of meaning and purpose. If every possible outcome occurs somewhere, then in some sense nothing you do matters, because every alternative also happens. You save someone's life in this universe, but fail to save them in another. You write a great novel here, but never write it there. Every achievement is matched by a failure, every joy by a sorrow, every version of reality by its opposite. Does that make life meaningless? Or does it mean that meaning is local, confined to individual branches, real for each version even if it's not universal across the multiverse? Different people find different implications here. Some find the multiverse comforting, the idea that every lost opportunity, every road not taken, actually is taken somewhere, that all possibilities are realized. If you wonder what your life would have been like if you'd made different choices, well, in the multiverse, those versions of you exist, and you can imagine their lives. Some find this liberating, a sense that existence is larger and richer than it appears, but others find it disturbing, even nihilistic, the sense that nothing is unique, nothing is special, every moment is diluted by infinite repetition and variation. And then there's the question of value. If there are universes where every possible outcome occurs, does that mean all outcomes are equivalent? If there's a universe where humanity thrives and a universe where it goes extinct, are they equally real and therefore equally valid? Most people would say no, that outcomes can be equally real without being equally good, that existence isn't the same as value. We can say that one universe is better than another in some moral or aesthetic sense, even if they're equally real. But the multiverse does seem to challenge certain ways of thinking about uniqueness and significance. Our universe isn't special in terms of being the only one, so any significance it has must come from its contents, from what happens here, not from its exclusive existence. I want to talk a bit about what cosmologists actually do when they think about the multiverse, because it's easy to get the impression that this is all just wild speculation, philosophical musing, without any connection to real science. And while there's definitely a speculative element, there's also serious scientific work being done, attempts to make the multiverse idea more precise, more testable, more connected to observation. One approach is to study the cosmic microwave background in great detail, looking for any anomalies that might hint at physics beyond the standard model or at interactions with other universes. The Planck satellite, which mapped the CMB with unprecedented precision, gave us data that scientists are still analyzing, looking for clues. Another approach is to study the distribution of matter in the universe, the large-scale structure of galaxies and galaxy clusters, and compare it to predictions from inflation and other theories. If we can pin down the details of how inflation worked, we might be able to determine whether eternal inflation is inevitable, and if it is, then the multiverse comes along as part of the package. There are also efforts to understand dark energy better, the mysterious force causing the universe's expansion to accelerate. The strength of dark energy, the cosmological constant, is one of those fine-tuning puzzles that the anthropic principle in a multiverse is supposed to help explain. If we can figure out more about what dark energy is and why it has the value it does, that might give us insight into whether the multiverse explanation is on the right track. And in quantum mechanics, there are ongoing efforts to understand decoherence, the process by which quantum systems interact with their environment and lose their quantum superposition, effectively becoming classical. Decoherence is crucial for many worlds because it explains why we don't experience superpositions directly, why the world appears classical to us, even though at the fundamental level it's quantum. Understanding decoherence better might help us understand how quantum branching works, whether it really produces separate worlds or whether there's some other interpretation that better fits the data. There's also work on quantum computing that's relevant here. Quantum computers work by exploiting superposition and entanglement, putting quantum bits in states that are in some sense multiple states at once, then manipulating those states to perform computations. Some proponents of many worlds argue that quantum computers are actually performing computations across many worlds simultaneously, that the speed up we get from quantum computing is because we're borrowing computational resources from parallel universes. That's a controversial claim, and many quantum information theorists don't buy it. But it's an interesting way to think about what quantum computation is doing and whether it gives us any insight into the nature of quantum reality. What's striking about all this work is that even though the multiverse itself might be unobservable, the theories that predict it are making contact with real observations, real experiments, real data. We're not just making up stories about parallel universes for fun. We're following the implications of our best theories and seeing where they lead, and sometimes they lead to places that seem strange and uncomfortable. But strangeness isn't a reason to reject an idea if the evidence points toward it. Science has a history of revealing that reality is weirder than we expected, and maybe the multiverse is just the latest example. Let me address some of the most common objections to the multiverse, because it's important to be fair to the critics and understand what they're worried about. One objection I mentioned earlier is the testability problem. The idea that if we can't observe other universes, we can't confirm or refute their existence, and therefore it's not science. I've talked about some responses to that, but it's worth emphasizing that this is a real concern, not something to be dismissed lightly. Science has worked well for centuries by sticking to observable phenomena and testable predictions, and relaxing that standard could potentially open the door to all kinds of unfalsifiable theories. If we accept the multiverse on the basis of theoretical elegance or indirect inference, what other unobservable entities might we accept for similar reasons? Ghosts? Supernatural forces? The slippery slope argument isn't always valid, but it's not always invalid either. Another objection is the fine-tuning argument cuts both ways. Yes, our universe seems finely tuned for life, and the multiverse offers an explanation. But the multiverse itself seems finely tuned. Inflation requires very specific initial conditions to get started, and the laws that govern the multiverse, the underlying framework of quantum mechanics or string theory or whatever, those laws seem precisely structured to allow for the complexity and diversity we see. So haven't we just pushed the fine-tuning problem back one level? Instead of asking why our universe is fine-tuned, we're asking why the laws that govern the multiverse are fine-tuned. And we can't solve that by invoking a multiverse of multiverses, can we? Or maybe we can, but then where does it end? Turtles all the way down. Some critics also argue that the multiverse is being used as a kind of intellectual crutch, an excuse to stop looking for deeper explanations. Instead of trying to understand why the constants have the values they do, we just say they're random across the multiverse, and we happen to be in a life-compatible one. But maybe there is a deeper reason, some underlying principle we haven't discovered yet, that explains the values. By appealing to the anthropic principle in a multiverse, we might be giving up too soon on finding a more satisfying answer. And historically, giving up on questions has rarely been productive. When people couldn't explain the motion of planets, they didn't say, well, maybe God just moves them that way and there's no deeper explanation. They kept looking and eventually found Newton's laws. Maybe the constants are like that. There's a reason we just haven't found it yet. There's also a more philosophical objection about the nature of existence. What does it mean for something to exist? The multiverse asks us to accept that there are countless universes we can never see, never interact with, never detect in any way. But if something has no causal connection to us, no way of ever affecting us or being affected by us, in what sense does it exist? Isn't existence at least partly about being able to interact, to make a difference? This gets into deep metaphysical questions about the nature of reality and existence, and different philosophical traditions give different answers. Some say that existence is fundamental and doesn't require detectability. Others say that existence without detectability is incoherent. It's not clear who's right. And let me be honest about something. A lot of physicists are uncomfortable with the multiverse for reasons that aren't purely scientific. There's an aesthetic dimension, a sense of what makes a good theory, and for many people, the multiverse just feels wrong. It feels like giving up on the unity and simplicity that physics has traditionally sought. Physics used to be about finding the one true description of reality, the single set of laws that explains everything. The multiverse says, no, there isn't one set of laws, there are infinitely many, each applying in different regions or branches. That's a very different kind of answer, and it's not the kind of answer that many physicists were hoping for. They wanted elegance, parsimony, a beautiful theory that explains everything with minimal assumptions. The multiverse seems the opposite. Maximum assumptions, infinite complexity, endless diversity. It's not what anyone would have chosen as the answer, which makes some people suspicious of it, even if they can't point to a specific flaw in the reasoning. But maybe that's the point. Maybe the universe or the multiverse doesn't care what we find aesthetically pleasing. Maybe reality is under no obligation to satisfy our preferences for elegance or simplicity or uniqueness. Maybe it just is what it is. And if that turns out to be a vast, diverse, infinite collection of parallel realities, well, we'll just have to get used to it. The history of science is full of times when human intuition and preference were wrong, when reality turned out to be stranger than we wanted it to be. The Earth isn't the center of the universe. Time isn't absolute. Particles are waves and waves are particles. Maybe the multiverse is just the next in a long series of humbling discoveries about our place in reality. Let's think about what it would mean if the multiverse is real and we someday confirm it, or at least become much more confident in it. How would that change things? Would it matter? On a practical level, probably not much. We'd still live our lives in this universe, still face the same challenges and opportunities. The existence of parallel realities wouldn't change the fact that we have to eat and sleep and work and form relationships, but on a psychological and philosophical level, it might matter quite a lot. It would represent a fundamental shift in how we understand our place in reality, comparable to the Copernican revolution, or the acceptance of deep time in geology. We'd know that our universe isn't all there is, that reality is vastly larger and more complex than the portion we can see. We'd know that our existence, while meaningful to us, is not unique, that countless variations play out elsewhere. That might make some people feel small and insignificant, but it might make others feel part of something larger, connected to a reality that's richer and more expansive than we imagined. It's hard to predict how such a discovery would affect human culture and thought, but it would certainly be one of the most profound discoveries in history, up there with evolution, heliocentrism, and the Big Bang itself. And there's a question about whether we'd ever really know for sure. Given the challenges of testing multiverse theories, it seems likely that even if physicists become increasingly confident that the multiverse is real, there will always be some uncertainty, some room for doubt. We might accumulate indirect evidence, multiple lines of reasoning that all point toward the multiverse, and eventually the weight of evidence becomes so strong that most scientists accept it. But there might never be a single decisive experiment, a clear observation that proves it beyond all doubt. We might have to learn to live with a certain level of uncertainty about the ultimate structure of reality, to accept that some questions can't be answered with complete confidence. But you know what? We already live with that uncertainty about lots of things. We're pretty confident that the sun will rise tomorrow, but we can't prove it with absolute certainty. We're very confident that evolution explains the diversity of life, but we weren't there to watch it happen. Science is always about building confidence through accumulated evidence, not about achieving absolute certainty. The multiverse might be another case where we build confidence gradually, where the theory becomes more and more accepted as we eliminate alternatives and as the implications of the theory match more and more observations. That's how science usually works, not through sudden revelations, but through slow accumulation of understanding. I want to circle back to something I mentioned earlier about the different types of multiverses and how they might relate to each other, because I think this is important for understanding the full picture. The quantum many-worlds multiverse, the inflationary bubble multiverse, the string theory landscape. These aren't necessarily incompatible. They could all be true simultaneously, different aspects of a larger reality. Maybe there's eternal inflation creating bubble universes, and within each bubble, quantum mechanics creates many worlds branching, and the bubbles explore different points in the string landscape. If so, the total multiverse would be even more vast and complex than any single version, a kind of super multiverse incorporating multiple types of parallelism. Or maybe only one of these pictures is correct, and the others are wrong or incomplete. Maybe eternal inflation doesn't really happen and there's only one universe at that level, but many worlds is still true, so there's a quantum multiverse but not a bubble multiverse, or vice versa. We don't know yet, the science isn't settled. And that's actually kind of exciting, isn't it? We're living in a time when these fundamental questions about the nature of reality are being actively investigated, when physicists are doing real work that might help us understand whether we live in a single universe or a multiverse, and if a multiverse, what kind. It's worth thinking about the history of how our conception of the universe has expanded over time, because the multiverse would be the latest in a long series of such expansions. Ancient humans thought the Earth was all there was, maybe with some celestial realm above. Then we realized there were other lands across the ocean, other continents, other people. Then we realized the sun was just one of countless stars, each potentially with planets of their own. Then we realized our galaxy was just one of countless galaxies, stretching billions of light years in every direction. At each step, we discovered that what we thought was everything was actually just a small part of something much larger. The multiverse would be another step in that progression, another expansion of our cosmic horizons, showing us that even the observable universe, vast as it is just one small piece of a much larger reality. And there's something almost poetic about that, isn't there? This continuous expansion of our understanding, this repeated discovery that we're smaller and less central than we thought. It's humbling, but it's also exhilarating. Each expansion has revealed new wonders, new complexities, new possibilities. If the multiverse is real, it would reveal the most extreme version of this yet. Not just more of the same, but actually different kinds of reality, different physical laws, different possibilities for existence. It's almost too much to take in, but that's what makes it fascinating. Let me talk about some specific scenarios that people have considered in multiverse theory, because these can help make the abstract ideas more concrete. One scenario is called the quantum suicide thought experiment, and it's designed to explore the implications of many worlds. Imagine a setup where you're connected to a quantum device that will kill you with 50% probability based on a quantum measurement. If many worlds is correct, then from your subjective perspective, you'll always survive, because there's always a branch where the device didn't kill you, and only that branch contains your continued consciousness. The branches where you died, well, you're not there to experience them. So from your point of view, it's as if you're immortal, always finding yourself in the branch where you survived. Now, this is a thought experiment, not something anyone should actually try, and there are lots of objections to the reasoning. For one thing, even if you always experience survival from your own perspective, that doesn't mean you're actually immortal in any meaningful sense, because in most branches you're dead, and the you that survives is just a diminishing slice of the overall set of yous across the multiverse. And there are questions about whether subjective probability works the way the thought experiment assumes, but it illustrates how weird things get when you take many worlds seriously and think about subjective experience in a branching reality. Another scenario involves the idea of Boltzmann brains. This is related to the inflationary multiverse and the question of what's most likely in an infinitely large or eternal universe. A Boltzmann brain is a hypothetical self-aware entity that forms spontaneously due to random quantum fluctuations. In an infinite universe, or one that lasts forever, quantum mechanics says that every possible configuration will eventually occur, no matter how unlikely. And it turns out that it's much more probable for a single brain to randomly fluctuate into existence, complete with false memories of a life and world that never existed, than for an entire universe with billions of brains to form. So, in an infinite multiverse, there should be vastly more Boltzmann brains than real brains like ours that formed through evolutionary processes. But we don't seem to be Boltzmann brains because our experiences are consistent with being in a real, ordered universe, not a random fluctuation. So this is actually a problem for some multiverse theories because they seem to predict that we're most likely Boltzmann brains, but we're not. This is called the Boltzmann brain problem, and it's one of the technical challenges for certain versions of the multiverse. Resolving it requires being careful about how you define probability and measure in an infinite multiverse, making sure that you're not counting Boltzmann brains as more likely than real observers. It's a technical issue, but it shows that multiverse theories have to be detailed and precise, not just vague hand-waving about infinite possibilities. There are also scenarios related to time travel and causality in a multiverse. If many worlds is correct, then maybe time travel doesn't create paradoxes, because when you travel back and change the past, you're not changing your original timeline, you're creating a new branch. You go back and prevent your grandfather from meeting your grandmother, but that just creates a branch where you were never born, while the original branch, the one you came from, still exists unchanged. So there's no paradox, no contradiction. This has been explored in fiction quite a bit, but it's also a serious idea in physics, a way to make sense of time travel without running into logical impossibilities. Though, of course, we don't know if time travel is actually possible. And most physicists think it probably isn't, at least not in the way science fiction usually portrays. I should mention that not all physicists who take the multiverse seriously think of it in exactly the same way. There are variations and different emphases, depending on which aspects you focus on. Some people are committed to many worlds but skeptical of eternal inflation. Others think eternal inflation is solid but aren't sure about many worlds. Some accept the mathematical plausibility of the string landscape, but doubt it's physically realized. The multiverse isn't a single unified theory that everyone either accepts or rejects in total. It's more like a family of related ideas, and different people have different levels of confidence in different parts. And that's actually healthy for science. We should have these disagreements and debates, these different perspectives and approaches. That's how we make progress, by having different people push in different directions and see what works, what leads to testable predictions, what makes sense. The danger would be if everyone decided the multiverse was definitely true and stopped questioning it, or if everyone decided it was definitely false and refused to consider it. The actual situation, where it's actively debated and investigated, is probably the best place to be right now. There's also an interesting connection between the multiverse and the question of why there's something rather than nothing. This is one of the oldest philosophical questions, and it's notoriously hard to answer. Why does anything exist at all? Why is there a universe rather than just nothingness? Some people think the multiverse makes this problem worse, because now you have to explain not just why there's one universe, but why there's an infinite multiverse. But others think it helps, because in a multiverse where every possibility exists, the existence of something rather than nothing is less surprising. If all possibilities are realized, then nothing is just one possibility among many. And it's not even clear that pure nothing is a coherent possibility, so maybe something is inevitable. This gets into very deep metaphysical territory, and I'm not sure there's a clear answer, but it shows how the multiverse connects to the biggest questions we can ask. Questions about existence itself, about why reality is the way it is. These aren't just scientific questions, but philosophical and maybe even theological ones, depending on your perspective. And that's part of what makes the multiverse so fascinating and so contentious. It straddles the boundary between science and philosophy in ways that make people uncomfortable. Let me try to bring this all together and think about where we are with the multiverse idea and where we might be going. We have several different lines of reasoning, several different theories that all suggest the existence of multiple universes. We have quantum mechanics and the many worlds interpretation. We have cosmic inflation and eternal inflation. We have string theory and the landscape. We have mathematical arguments about infinity and possibility. None of these are proven, none are certain, but they're all serious ideas with serious arguments behind them, developed by serious scientists and mathematicians who aren't just making things up. At the same time, we have significant objections and challenges. The testability problem, the fine-tuning of the multiverse itself, the philosophical questions about existence and identity, the aesthetic concerns about the nature of scientific theories. These aren't trivial objections, and they haven't been fully resolved. So we're in this interesting position where we have strong reasons to take the multiverse seriously, but also strong reasons to be cautious and skeptical. What happens next probably depends on both theoretical developments and observational discoveries. On the theoretical side, we need better understanding of quantum mechanics, better formulations of eternal inflation, progress on string theory, or whatever theory ultimately replaces or extends it. We need to address the technical problems like the measure problem and the Boltzmann brain problem. We need clearer thinking about how to test multiverse theories and what would count as evidence for or against them. On the observational side, we need better data on the cosmic microwave background, better understanding of dark energy, better tests of quantum mechanics in extreme conditions. We need to look for any possible signatures or effects that might hint at physics beyond what we currently know. And maybe in the decades to come, the evidence will point clearly one way or the other. Maybe we'll find strong indirect evidence for the multiverse through its theoretical necessity in our best theories combined with tests of those theories. Or maybe we'll find reasons to reject the current theories that predict the multiverse and develop new theories that don't require it. Or maybe, and this seems likely to me, we'll remain in a state of informed uncertainty, with different physicists having different levels of confidence, but no definitive answer that everyone accepts. But here's the thing, and I think this is really important: the question matters. Regardless of whether the multiverse turns out to be real, the fact that we're asking this question, the fact that we've reached a point in our scientific development where we can seriously consider such ideas, that's remarkable. A century ago, we didn't even know there were other galaxies. Now we're asking whether there are other universes. That's an astonishing expansion of our capacity to investigate reality, to ask questions that previous generations couldn't even formulate. And even if the multiverse turns out to be wrong, even if future discoveries show that we live in a single universe after all, the process of investigating the question will have taught us things. We'll have learned more about quantum mechanics, more about cosmology, more about the foundations of physics. We'll have pushed the boundaries of what we can know and tested the limits of scientific methodology. That's valuable in itself, regardless of the answer. So where does that leave us, standing here in the early 21st century, contemplating the possibility of infinite parallel realities? It leaves us in a position of extraordinary privilege and extraordinary uncertainty. We have the tools and knowledge to ask these profound questions, but not yet the tools or knowledge to answer them definitively. We can see far enough to know that there are deep mysteries, but not far enough to resolve them completely. And maybe that's always been the human condition, always will be. We push back the boundaries of ignorance, only to discover new questions, new mysteries, new horizons. The multiverse, if it's real, would be the ultimate expansion of those horizons, not just more space, not just more time, but actually more realities, more possibilities, more existence than we can ever directly experience. It would mean that the universe we see, as vast as it is just one tiny corner of something incomprehensibly larger. It would mean that every moment, every choice, every quantum fluctuation is part of an infinite branching tree of actualizations, all equally real, all equally part of the totality of existence. It's almost impossible to fully grasp, almost impossible to integrate into our everyday understanding of life and meaning. but maybe we don't need to fully grasp it. Maybe it's enough to know that reality is larger and stranger than we thought, that our little corner of existence is part of something grander, that the universe, or the multiverse, contains more possibilities than we can imagine. Maybe that sense of vastness, of mystery, of endless frontier, maybe that's what we need. Not certainty, not complete understanding, but the knowledge that there's always more to discover, always deeper questions to ask, always new horizons to explore. And I think that's what makes us human, what makes us different from any other creature we know of. We're not content with just surviving, just existing in our local environment. We want to know, to understand, to push beyond the boundaries of immediate experience and ask what's really out there, what reality is really like at its deepest level. We build telescopes to see distant galaxies. We build particle accelerators to probe the smallest scales. We develop theories and models to make sense of it all. And sometimes those theories lead us to conclusions that seem impossible, that challenge everything we thought we knew. The multiverse is one of those conclusions. It emerged from the equations, from taking seriously the mathematics of our best theories. Nobody wanted it, nobody expected it, but there it is, staring at us from the pages of physics papers and cosmology textbooks, asking us to consider that everything we can see might be just the tiniest fraction of what exists. And we're still figuring out how to think about that, how to test it, whether to believe it. But we're doing the work, asking the questions, following the evidence wherever it leads. Maybe in 100 years, this will all seem obvious. Future students will learn about the multiverse the way students today learn about galaxies or atoms, as established features of reality that we've confirmed through observation and theory. Or maybe in 100 years, the multiverse will be a historical curiosity, an interesting idea that turned out to be wrong, a detour on the path to deeper understanding. I don't know. Nobody knows. But the fact that we can ask the question, that we can investigate it seriously using the tools of mathematics and physics, that's something worth celebrating. Because at the end of the day, whether there's one universe or infinitely many, whether we're alone or surrounded by infinite versions of ourselves in parallel realities, we still have this moment, this experience, this particular version of existence to live. And that has to be enough, doesn't it? We can wonder about other possibilities, other universes, other versions of reality, but we can only live this one, make our choices in this branch, experience this particular manifestation of existence. And maybe that's the answer to the question of meaning in a multiverse. Meaning is local, personal, real for each version, even if it's not universal. The fact that other possibilities exist somewhere doesn't diminish the reality of this possibility, this moment, this universe. So maybe the multiverse, if it's real, doesn't change anything about how we should live, what we should value, how we should treat each other. We still have to find meaning and purpose in our lives, still have to make choices and live with consequences, still have to care about what happens even if other outcomes occur elsewhere. The vastness of the multiverse doesn't excuse us from the responsibility of living well in this universe, in this moment. If anything, it might make that responsibility more clear, more precious, because this particular configuration of reality, this particular version of existence, it's unique even in an infinite multiverse. This specific moment will never occur exactly this way anywhere else. That makes it special, makes it worth paying attention to, makes it worth living fully. And perhaps that's the final lesson, the real insight that comes from contemplating the multiverse. Not that nothing matters because everything happens somewhere, but that everything matters precisely because this particular happening, this particular configuration, is unique and unrepeatable. The multiverse doesn't dilute meaning, it concentrates it, focusing our attention on the irreplaceable value of this moment, this experience, this version of reality that we're privileged to inhabit. We're here now in this universe with this particular arrangement of matter and energy, this particular set of experiences and possibilities. And that's not diminished by the existence of other universes. If anything, it's enhanced by it, given greater context and greater significance. So I think the multiverse, whatever its ultimate truth status, is valuable as a concept, as a possibility to contemplate. It expands our thinking, challenges our assumptions, forces us to consider what we mean by existence and reality and significance. It pushes the boundaries of science and philosophy, asking us to think harder about what we can know and how we can know it. And it reminds us that reality is probably stranger, richer, more complex than anything we've yet imagined. That's a good reminder to have, a useful bit of intellectual humility in the face of the cosmos. We don't have it all figured out, we probably never will, but we keep trying, keep investigating, keep asking questions, and maybe someday we'll know for sure whether the multiverse is real, or maybe we won't. But the journey of finding out, the process of investigation, the willingness to consider even the wildest possibilities if the evidence points that way, that's what science is about, that's what makes us human, and that's something worth celebrating regardless of where it leads. Now, let's move on to another theory for you to reflect on. I've been thinking a lot about connections lately, and it's one of those things that seems so obvious at first, like, of course things are connected, we can see connections everywhere, but the more you dig into it, the more you realize that the depth and extent of these connections, the sheer intricacy of how everything in the universe relates to everything else, well, it's far more profound and far stranger than we typically imagine. And what's really fascinating is that this isn't just some poetic notion, some philosophical abstraction that sounds nice but doesn't mean much. It's actually deeply, fundamentally true in ways that physics and biology and mathematics and even social science have revealed to us over the past century or so. Everything really is connected, not metaphorically, actually connected. And when you start to understand how and why, it changes the way you see, well, everything. Think about your morning coffee for a second. Just that simple cup of coffee you might have had today. You might think it's just a drink, right? Just you and your coffee. But that coffee, that single cup, connects you to rainforests in Ethiopia or Colombia, to farmers whose names you'll never know, to shipping routes that cross oceans, to the labor of countless people, to the soil and the organisms in that soil, to the climate patterns that allowed those coffee plants to grow, to the bees or other insects that pollinated the flowers that became the cherries that held the beans. And that's just the beginning, really. Because the cup itself, that ceramic or paper cup that connects you to clay deposits or paper mills, to the energy grid that fired the kiln or processed the pulp, to the trees that became that paper, to the forest ecosystem those trees were part of, the water you used that connects you to the water cycle, to clouds and rain and rivers and underground aquifers, to the treatment plants and pipes and infrastructure of your city. And we haven't even talked about the energy you used to heat it, the electricity or gas that connects you to power plants or gas fields or solar panels, to the vast grid of energy distribution, to the miners who extracted coal or uranium, to the engineers who designed the systems. One cup of coffee and you're already connected to thousands of people, to ecosystems on multiple continents, to geological processes, to the water cycle, to the energy grid, to global economic systems of trade and currency. And that's just your coffee. That's just one moment of one morning. But here's the thing, and this is where it starts to get really interesting. These connections aren't just practical or economic. They're not just about supply chains and trade routes, though those are fascinating in their own right. The connections go much, much deeper. They're woven into the very fabric of reality itself, into the laws of physics, into the structure of matter and energy, into the nature of information and causality. You see, when physicists and biologists and mathematicians started really looking at how the universe works, what they found was that isolation, the idea of things being truly separate and independent, that's actually the illusion. Connection is the reality. Separation is what we have to work hard to maintain artificially, temporarily. The natural state of things is interconnection. Let's start with something really fundamental, something that seems almost too basic to mention but turns out to be profound when you think about it carefully. Causality, the fact that one thing can affect another thing. That's a connection, right? That's maybe the most fundamental connection there is. You push a door and it opens, a storm drops rain and the river rises, the sun shines and plants grow. Cause and effect, action and reaction, one thing leading to another. And you might think, well, sure, but that's just how things work. That's not really what we mean by connection. But actually it is, because causality means that nothing happens in isolation. Every event, every action, every change is connected to other events, other actions, other changes. Nothing just happens by itself, spontaneously, without cause. Everything that occurs is the result of something else that occurred, and will in turn become the cause of something else that will occur. It's an endless chain, an infinite web of causality stretching back to the beginning of time and forward to the end, if there is an end. And that web of causality, it's not simple or linear. It's not like dominoes falling in a neat line, one thing causing one other thing. It's more like, imagine a vast network, billions and trillions and more connections than you can possibly count, where every event is caused by multiple other events and causes multiple future events, where the connections branch and merge and loop back on themselves in patterns of staggering complexity. You do something small, you make some minor choice or action, and it ripples out through this network in ways you can never fully predict or understand, touching other lives, other events, other outcomes that you'll never even know about. That's chaos theory in a sense. That's the butterfly effect that everyone's heard about. The idea that a butterfly flapping its wings in Brazil could theoretically set off a chain of events that leads to a tornado in Texas weeks later. And while that specific example is a bit oversimplified, the principle behind it is absolutely real and has been demonstrated mathematically and observed in nature countless times. The butterfly effect comes from meteorologist Edward Lorenz, who in 1961 was running computer simulations of weather patterns, trying to model how the atmosphere behaves. And he made this fascinating discovery, this thing that seems small but turned out to be revolutionary. He was running a simulation and wanted to check something in the middle of it, so he stopped the program and restarted it from that midpoint, typing in the numbers where he'd left off. But he rounded the numbers slightly, just a tiny bit. We're talking about the difference between, say, 0.506127 and 0.506. Incredibly small differences in the initial conditions. And what he found was that the weather patterns that emerged from these two slightly different starting points, they diverged completely. They became totally different weather systems. And that shouldn't happen, right? If you change something by just a tiny, tiny amount, the result should only change by a tiny amount. That's how most of the universe seems to work. But in certain systems we now call chaotic systems, tiny changes in initial conditions can lead to enormous differences in outcomes. The system is so sensitive to those initial conditions, so interconnected in its behavior, that you can never really predict what will happen far into the future, because you can never measure the starting conditions with perfect precision. You're always off by some tiny amount, and that tiny amount, through the web of connections and causes and effects, grows and grows until it completely changes the outcome. And weather is like this. The atmosphere is a chaotic system. So is the economy. So are ecosystems. So are populations of organisms. So is your brain, actually, the way neurons fire and connect and create thoughts and consciousness. All of these are systems where everything is connected to everything else in such intricate ways that small changes propagate and amplify and create unpredictable outcomes. And that's not a flaw or a bug in how these systems work. It's a fundamental feature of interconnection. When things are deeply connected, when they influence each other in complex ways, sensitivity and unpredictability emerge naturally. You can't have dense connection without chaos, without this sensitivity to initial conditions. But let's go even deeper, because there's another kind of connection that's even more fundamental, even more strange. And this is where we get into quantum mechanics, into the really weird stuff that modern physics has revealed about the nature of reality. You see, at the quantum level, at the scale of atoms and subatomic particles, connection takes on this utterly bizarre quality that Einstein himself found so disturbing, he spent years trying to prove it couldn't be real. It's called quantum entanglement, and it's one of the most thoroughly tested and experimentally confirmed phenomena in all of physics. And it's also one of the strangest things we've ever discovered about the universe. Here's how it works, or at least here's how we understand it, which is honestly still a bit mysterious even to physicists who work with it every day. When two particles interact in certain ways, they can become entangled. And what that means is that their properties become correlated in a way that transcends normal causality. If you measure one particle and find it has a certain property, say it's spinning in a particular direction, then the other particle, no matter how far away it is, will instantly have a corresponding property. The particles are connected, linked in a way that isn't mediated by any signal or force traveling between them. There's no message being sent, no information passing from one to the other at light speed or any other speed. The connection is instantaneous and it persists across any distance. You could have one particle on Earth and the other on the far side of the galaxy, and they'd still be connected in this way. Measure one, and you instantly know something about the other. Now, Einstein called this spooky action at a distance, and he hated it because it seemed to violate the principle that nothing can travel faster than light, which is a cornerstone of relativity. And he proposed that there must be some hidden variables, some properties of the particles we just haven't measured yet, that would explain the correlation without requiring this instantaneous connection. But here's the thing, and this is what's so profound about this. Experiments have been done, starting with John Bell in the 1960s, who came up with a way to test this, and then later with Alain Aspect and others who actually performed the tests, and what they found was that Einstein was wrong. There are no hidden variables. The connection is real. Entangled particles really are connected in this deep, non-local way that transcends space and time as we normally understand them. And you might be thinking, okay, that's weird, but that's just tiny particles doing strange quantum things that doesn't affect me or the world I experience. But actually it does, because everything is made of these particles. You are made of quantum particles. Your brain, your body, every atom in you was once entangled with other atoms and may still be entangled with particles scattered throughout the universe. Now, for complicated reasons involving something called decoherence, these quantum effects mostly don't show up at the scale of everyday life. The connections get washed out by interactions with the environment, by the sheer complexity of large systems, but they're still there, underlying everything. And in some cases, they actually do affect things at larger scales. There's growing evidence that quantum entanglement plays a role in photosynthesis, in how plants capture light energy. It might play a role in how birds navigate using the Earth's magnetic field. It might even play a role in consciousness, though that's much more speculative and controversial. But whether or not quantum effects show up directly in our daily experience, the point is that at the most fundamental level of reality, connection isn't something that happens between things. Connection is built into the fabric of what things are. Particles aren't separate entities that then sometimes interact. They're nodes in a vast web of relationships and correlations that extends throughout the entire universe. The universe at the quantum level is not a collection of separate objects. It's a unified, interconnected whole. You can't even really talk about individual particles in isolation. You can only talk about the relationships between them, the patterns of correlation and entanglement that link them together. And this gets at something really profound, something that's not just physics, but philosophy. What is a thing, really? What does it mean for something to be a distinct, separate entity? We like to think of objects as having clear boundaries, as being self-contained and independent. This is a table, that's a chair, I'm me and you're you, and we're all separate things that happen to interact sometimes. But the more closely you look, the more you realize those boundaries are fuzzy, arbitrary, convenient fictions we impose to make sense of the world. Where does the table end and the air begin? At the surface, you might say. But the surface is where molecules of the table are constantly interacting with molecules of the air, where they're exchanging heat and sometimes particles, where the boundary is actually a zone of intense connection and exchange. And the molecules themselves, they're made of atoms that are mostly empty space, with tiny nuclei and electron clouds that don't have sharp edges. And those atoms are exchanging photons with their environment all the time, absorbing and emitting light, interacting with electromagnetic fields. So where exactly is the boundary? When you look closely enough, the boundaries dissolve. What remains is a pattern of relationships, a node in a network, a temporary, localized concentration of energy and information that we find it useful to label as an object. You are not separate from your environment. You are a process, a dynamic pattern of matter and energy and information that maintains itself by constantly exchanging with its surroundings. You breathe in air, and some of those molecules become part of you, incorporated into your cells. You breathe out carbon dioxide, and those molecules came from you, but are now part of the atmosphere. You eat food, and that food, which was recently part of other organisms, plants, or animals, becomes you. Your cells break it down, incorporate it, use it to build new proteins and membranes and organelles, and then you excrete waste, you shed skin cells, you lose hair, you cry tears, you sweat, and all of that, which was recently you, becomes part of the environment again. Over time, every atom in your body is replaced. The carbon in your bones, the iron in your blood, the calcium in your teeth, none of it is permanent. It cycles through you, spending some time as part of the pattern we call you before moving on to be part of something else. In a very real sense, you are not a thing. You are a process, a wave of organization passing through matter, a pattern that persists even as the substance constantly changes. And this is true not just of you as an individual organism, but of everything. The Earth itself is not a static object. It's a dynamic system where matter and energy are constantly cycling and flowing. The atmosphere, the oceans, the crust, the mantle, the core, they're all connected in cycles of movement and exchange. Water evaporates from the oceans, forms clouds, falls as rain, flows through rivers and underground aquifers, and returns to the ocean. Carbon cycles through the atmosphere, through living organisms, through the soil, through rocks, through the ocean, over time scales ranging from years to millions of years. Nitrogen cycles through the atmosphere, through bacteria that fix it into forms plants can use, through plants and animals, through decomposition, back into forms that return to the atmosphere. These are called biogeochemical cycles, and they link the living and non-living components of the Earth into a single, interconnected system. And living things, organisms, they're not just passive participants in these cycles. They actively shape them, they drive them, they create and maintain the conditions that make life possible. This is the Gaia hypothesis, proposed by James Lovelock in the 1970s. The idea that the Earth's biosphere, all of life taken together, acts in some sense like a single organism that regulates the planet's environment to keep it habitable. Now, this was controversial when first proposed, and in its strong form, the idea that the Earth is literally a single organism with intentions and purposes, it's probably too strong, too anthropomorphic. But in a weaker form, the idea that life and environment are deeply interconnected and co-evolving, shaping each other in feedback loops, that's now widely accepted. Life doesn't just adapt to the environment, it creates the environment. The oxygen in the atmosphere, for example, that's a product of photosynthesis, of billions of years of plants and algae and cyanobacteria producing oxygen as a waste product. The atmosphere we breathe, the air that seems like just a passive backdrop to life, is actually a creation of life maintained by life and would be radically different without life. And ecosystems, when you look at how they function, they're extraordinary examples of interconnection at work. You have all these different organisms, plants and animals and fungi and bacteria, all living together, all depending on each other in intricate ways. Plants produce energy through photosynthesis, converting sunlight into chemical energy stored in sugars and starches. Herbivores eat the plants, carnivores eat the herbivores, and when anything dies, decomposers break it down, returning nutrients to the soil where plants can use them again. That's the basic food web, but it's so much more complex than that simple description suggests. You have symbiotic relationships where different species cooperate for mutual benefit. You have parasites and pathogens. You have competition for resources. You have predator-prey dynamics that oscillate in complex cycles. You have keystone species whose presence or absence can reshape the entire ecosystem. Remove wolves from Yellowstone, which happened in the 1920s, and the ecosystem changed dramatically. Elk populations exploded without their main predator. They overgrazed, vegetation declined, stream banks eroded, beaver populations crashed because they needed the vegetation, and that affected fish and birds and countless other species. The whole system shifted into a different state. Then, when wolves were reintroduced in the 1990s, the ecosystem began recovering. The elk population came back into balance, vegetation returned, streams stabilized, beavers returned, and the ripple effects went through the entire system. That's called a trophic cascade, and it's a dramatic example of how connected everything is in an ecosystem. You can't just add or remove one species without affecting everything else. And underneath the plants and animals, we can see there's this whole hidden network of connection that we've only recently started to understand, and it's beautiful and strange and changes how we think about forests and ecosystems entirely. It's the mycorrhizal network, the fungal connections between trees. You see, most plants, especially trees, form partnerships with fungi in the soil. The fungi attach to the tree roots, and they exchange resources. The tree provides the fungus with sugars from photosynthesis, and the fungus provides the tree with water and nutrients, especially nitrogen and phosphorus, that the fungal networks can access and transport much more efficiently than roots alone. And here's the amazing part. These fungal networks don't just connect one tree to one fungus. They connect tree to tree, creating an underground web of communication and resource sharing. A tree that's in a sunny spot producing lots of sugar, through photosynthesis can share some of that sugar through the fungal network with a tree in shade that's struggling. A tree that's dying can send its resources through the network to younger trees, passing along not just nutrients, but some research suggests even information, chemical signals about threats like insects or disease. The forest is not a collection of individual trees competing for resources. It's a community, a network, a kind of superorganism where individuals are connected and in some sense cooperating. This was discovered and extensively studied by Suzanne Simard, a forest ecologist, and her work has really transformed how we understand forest ecosystems. She found that big old trees, which she calls mother trees, are the hubs of these networks, the most connected nodes, and they play a crucial role in nurturing younger trees and maintaining the health of the forest. Remove the mother trees, clear cut them, and the whole network suffers. The forest doesn't just lose individual trees, it loses the connections, the web of support that makes the ecosystem resilient. And this mycorrhizal network isn't unique to forests. It exists in grasslands, in agricultural fields, everywhere plants and fungi coexist. Under your feet right now, unless you're on concrete or bare rock, there's likely a hidden network of fungal threads connecting the plants around you, sharing resources, transmitting signals, creating a living internet of roots and mycelium. And speaking of the internet, let's talk about human networks for a bit, because we've created our own version of interconnection, our own web that spans the planet and connects billions of people in ways that would have seemed like magic just a few generations ago. The internet is maybe the most visible, most tangible example of connection in modern life. You can send a message to someone on the other side of the world and they'll receive it in seconds. You can access information from libraries and databases and servers scattered across continents. You can watch a video uploaded by someone in Japan while you're sitting in Brazil. You can collaborate on a document with colleagues in different countries, editing it simultaneously, seeing changes appear in real time. The internet has made the world smaller, has collapsed distance in ways that are historically unprecedented. But the internet isn't just a tool we use, it's also a model, a metaphor, a way of understanding other kinds of networks. Because networks, it turns out, have certain properties, certain patterns that show up again and again in completely different contexts. Social networks, neural networks in brains, metabolic networks in cells, food webs in ecosystems, the structure of the internet itself, they all share common features. They all tend to have what's called a scale-free structure, where most nodes have relatively few connections, but a small number of nodes, the hubs, have a huge number of connections. Think of social networks. Most people know and regularly interact with maybe 50 to 150 people, but there are a few individuals, celebrities, influencers who are connected to millions. The same pattern shows up in the internet, where most websites have few links to them, but sites like Google or Wikipedia have links from millions of other sites. It shows up in metabolism, where most chemical compounds participate in just a few reactions, but a few key compounds like ATP or water are involved in countless reactions. This scale-free structure emerges naturally in growing networks through a process called preferential attachment, where new nodes are more likely to connect to nodes that already have many connections. The rich get richer, the connected get more connected, and you end up with this characteristic pattern of a few super-connected hubs and many sparsely connected nodes. And this structure has interesting properties. It makes networks robust to random failures. You can remove most nodes randomly and the network will still function because most nodes aren't that important. They're not critical to keeping everything connected. But it also makes networks vulnerable to targeted attacks. Remove the hubs, the highly connected nodes, and the network can fragment, can break apart into isolated pieces. This is true for the internet. If you could take down the major routing hubs, you'd cripple connectivity. It's true for ecosystems. If you remove keystone species, the hubs of the food web, the ecosystem can collapse. It's true for social movements. If you can identify and neutralize the key organizers, the hubs of the social network, you can disrupt the movement. Understanding network structure isn't just an abstract mathematical exercise. It has real consequences for how systems function, how they fail, how they can be protected or attacked. And social networks specifically, the networks of human relationships and communication, they have this fascinating property that's been studied extensively. It's called the small world phenomenon, or more popularly, 6 degrees of separation. The idea is that even though there are billions of people on Earth, any two people are connected by a surprisingly short chain of acquaintances. You know someone who knows someone who knows someone, and usually by the time you get through 5 or 6 steps like that, you can connect any 2 random people on the planet. This was first explored scientifically by Stanley Milgram in the 1960s with his famous small world experiment. He asked people in the Midwest to try to get a package to a target person in Boston, but they could only send it to someone they knew personally, and then that person had to send it to someone they knew, and so on. And on average, it took about 6 steps to get the package to the target, 6 degrees of separation. Now, the actual number varies depending on how you define connection and what population you're looking at. And Milgram's study had some methodological issues, but the basic finding has been replicated in many contexts. Facebook did a study in 2011 looking at their social graph, all the friendships on their platform, and found that on average, any 2 users were connected by about 4.74 steps. The world is smaller, more connected than our intuition suggests. And this has profound implications. It means that what happens to someone far away, someone you've never met, might not be as distant as you think. You're connected to them through chains of relationship and influence, and what affects them can ripple through those chains to affect you. An economic crisis in one country can spread to other countries through trade relationships and financial networks. A disease emerging in one region can become a global pandemic through travel and contact networks. An idea, a meme, a piece of information can spread virally through social networks, reaching millions of people in days or hours. We live in a connected world, and that connection has both benefits and risks. Information and resources can flow quickly to where they're needed, but so can crises and contagion. You can't have the benefits of connection without also accepting the vulnerabilities that come with it. And your brain, the thing that's reading these words right now and making sense of them, that's also a network, arguably the most complex network we know of in the universe. 86 billion neurons, each connected to thousands of other neurons through synapses, creating a web of connections so dense and intricate that we're still trying to understand how it produces consciousness and thought and memory and emotion and all the other things minds do. And what's fascinating is that the brain isn't just a passive network where signals travel along fixed pathways. It's a dynamic, plastic network that constantly rewires itself based on experience. When you learn something new, when you practice a skill, when you form a memory, the connections in your brain change. Some synapses get stronger, some get weaker, new connections form, old ones are pruned away. The pattern of connectivity itself is the information, is the memory, is the skill. You are, in a very literal sense, the pattern of connections in your brain. Your personality, your knowledge, your abilities, your sense of self, all of it emerges from the structure and dynamics of this neural network. And consciousness itself, that subjective feeling of being you, of experiencing the world, that's still deeply mysterious, one of the great unsolved problems in science and philosophy. But whatever consciousness is, it seems to be a product of connection, of integration, of different parts of the brain, communicating and coordinating with each other. When you're conscious, information is flowing throughout the brain, different regions are synchronized in their activity. There's a kind of unity, a coming together of disparate processes into a single integrated experience. When that integration is disrupted, say during deep sleep or under anesthesia, consciousness fades. The parts of your brain are still active, still processing information, but they're not connected in the right way, not integrated. And so there's no unified experience, no sense of self. Connection, it seems, is essential to consciousness. You're not conscious because of any single neuron or any single brain region. You're conscious because of the pattern of connections between billions of neurons across many brain regions, all working together, all communicating, all integrated into a single coherent system. Now let's zoom back out and think about connection at the largest scales, at the scale of the universe itself. Because even the cosmos, vast and mostly empty as it seems, is deeply interconnected. You've probably heard that we're made of stardust, right? That's not just a poetic metaphor. It's literally true. Most of the atoms in your body, the carbon and nitrogen and oxygen and all the others except hydrogen and some helium, they were created in the cores of stars billions of years ago. You see, when the universe began in the Big Bang about 13.8 billion years ago, it was just hydrogen and helium and traces of lithium, the simplest elements. But stars, through nuclear fusion, create heavier elements. In the cores of stars, hydrogen fuses to make helium, helium fuses to make carbon and oxygen, and in the most massive stars, this process continues up through the periodic table, creating iron and silicon and magnesium and sulfur and all the other elements. And then, when those massive stars die, they explode as supernovae, and those explosions scatter those newly created elements out into space, where they mix with the interstellar medium, the gas and dust between stars. And eventually, that enriched material collapses under gravity to form new stars and planets. Our solar system formed about 4.6 billion years ago from a cloud of gas and dust that contained elements created in previous generations of stars. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of it was forged in the heart of a dying star, scattered into space in a supernova explosion, and then recycled into the molecular cloud that became our solar system. You are not separate from the stars. You are made of them. You are the universe become conscious, matter organized in such a way that it can reflect on itself. And this cosmic recycling, this connection between us and the stars, it's ongoing. Right now, as you read this, cosmic rays are passing through your body, high energy particles that were accelerated in supernovae or in the jets of black holes, traveling across the galaxy or even across the universe before hitting Earth and passing through you. Neutrinos, those ghostly particles that barely interact with matter, are streaming through you constantly, billions of them every second, coming from the sun and from distant cosmic events. You are bathed in radiation from the cosmic microwave background, the afterglow of the Big Bang itself, photons that have been traveling for nearly 14 billion years, carrying information about the early universe. You are connected physically, materially, to the entire history of the cosmos. And the forces that govern the universe, the four fundamental forces, gravity and electromagnetism, and the strong and weak nuclear forces, they also connect everything. Gravity reaches across the entire universe, every mass attracting every other mass, no matter how distant. The sun's gravity keeps Earth in orbit. The moon's gravity creates tides in our oceans. The gravity of the Milky Way holds the solar system in orbit around the galactic center. The gravity of our local group of galaxies holds the Milky Way and Andromeda and dozens of smaller galaxies together. And the gravity of distant superclusters of galaxies affects the structure and motion of everything in the observable universe. Gravity connects everything that has mass, and everything has mass, so everything is gravitationally connected to everything else. Electromagnetism, similarly, creates connections through electric and magnetic fields. When you look at something, you're connected to it electromagnetically. Photons, particles of light, are being emitted or reflected by that object, traveling through space and being absorbed by the photoreceptors in your eyes. That's how you see, through an electromagnetic connection between you and everything you look at. When you feel warmth from the sun or from a fire, that's infrared radiation, electromagnetic waves carrying energy to you. When you listen to the radio or use your phone, that's electromagnetic waves carrying information through space. The electromagnetic force is what holds atoms and molecules together, what creates chemistry and material properties and all the structure we see in the world. Without electromagnetism, there would be no atoms, no molecules, no chemistry, no life. everything would just be a diffuse gas of elementary particles, and the nuclear forces, though they operate only at tiny distances inside atomic nuclei, they're what make matter stable, what allow atoms to exist at all. The strong nuclear force binds quarks together into protons and neutrons, and binds protons and neutrons together into nuclei. Without it, there would be no atoms, just a soup of quarks and leptons. The weak nuclear force governs radioactive decay and is crucial for the fusion reactions in stars. Without it, the sun wouldn't shine, stars wouldn't produce the elements we're made of. The universe would be a dark, cold, sterile place. These forces, these fundamental interactions, they're the basis of all connection in the physical universe. Everything that happens, every interaction, every change, comes down to these forces acting between particles, creating patterns, creating structure, creating the complex interconnected world we experience. And there's another way everything is connected that's maybe more abstract but equally profound, and that's through information. Information is a kind of currency, a way of describing patterns and order and structure. And information flows, it propagates, it spreads from place to place, from system to system. When you learn something, information is flowing into your brain, changing the pattern of connections there. When you communicate with someone, information flows from you to them, changing their knowledge, potentially changing their behavior. When genes are passed from parents to offspring, information encoded in DNA flows from one generation to the next, carrying instructions for building organisms. When light from a distant star reaches Earth, information about that star, its composition and temperature and motion, flows to us across the void of space. The universe is not just matter and energy, it's also information, patterns that mean something, that have consequences, that shape what happens. And information, once created, doesn't just disappear. It can be transformed, it can be copied, it can degrade or become scrambled, but in some form it persists. There's even a principle in physics related to quantum mechanics and black hole thermodynamics that information is fundamentally conserved, that the total information content of the universe is constant. This leads to puzzles like the black hole information paradox, which asks what happens to the information about matter that falls into a black hole. Does it get destroyed, which would violate information conservation, or does it somehow escape encoded in the radiation the black hole emits? We don't fully understand the answer yet, but the question itself reveals how deep the connection between information and physical reality goes. Information isn't just an abstract concept, something that exists in books or computers or brains. It's a fundamental feature of the universe, as real and as conserved as energy. Let's think about time for a moment and how it connects things. Causality, as we talked about earlier, is fundamentally temporal. It's about one event leading to another event later in time. The past causes the present causes the future, and this creates a chain, an arrow of time connecting everything that has happened to everything that will happen. You are connected to the Big Bang, not just because you're made of matter and energy that came from the Big Bang, but because you are part of the causal chain that started with the Big Bang. Everything about you, your existence, your form, your thoughts right now, all of it traces back through an unbroken chain of causes and effects to the very beginning of the universe. And you are connected forward in time too. Your actions now will have consequences, will cause things to happen in the future. And those future events will cause other events and so on, rippling forward through time long after you're gone. But time connection isn't just about causality. It's also about correlation, about the fact that the state of the universe at one time is related to its state at other times. The laws of physics are time symmetric in many respects, meaning that if you know the exact state of a system now, you can, in principle, predict its future states and retrodict its past states. Everything is connected through time by the mathematical structure of physical law, by the equations that govern how things change. Now, in practice, this predictability is limited by chaos, by quantum uncertainty, by our inability to know the exact state of anything. But the connection is still there, in principle, in the fabric of physical law. And there's a way of thinking about the universe coming from some interpretations of relativity and quantum mechanics, where all of time, past, present, and future, exists in some sense simultaneously as a single four-dimensional structure called space-time. In this view, the universe is not changing, not evolving through time, but rather just is, a complete, eternal, unchanging four-dimensional object. Your entire life, from birth to death, is a trajectory through this four-dimensional space-time, a kind of static pattern, a line or tube that exists all at once. This is called the block universe view, and while it's philosophically controversial, it's consistent with the mathematics of relativity. If this view is correct, then you're connected not just to other things in space, and not just to other times through causality, but to your entire life, to every moment you've ever experienced or will experience, all of which exists simultaneously in the structure of space-time. And this raises profound questions about the nature of self and identity. If all moments of your life exist simultaneously, then in what sense are you changing? In what sense is there a you that persists through time? One way to think about it is that you're not a thing, but a process, a pattern extended through time. You at age 5 and you at age 50 are not the same in any material sense. Almost every atom has been replaced. Your body and mind are completely different. But there's continuity, there's a causal connection, a persistence of pattern that makes them both you. You are a four-dimensional object, a space-time worm, a trajectory through reality that maintains certain characteristic patterns even as it changes. And just like you can't separate yourself from your environment spatially, you also can't separate yourself from your history temporally. You are not just what you are now. You are everything you have been and everything you will be, all connected, all part of the same extended process. Let's talk about emergence for a bit, because this is crucial for understanding how connection creates complexity and novelty. Emergence is the phenomenon where a system as a whole has properties or behaviors that its individual parts don't have, properties that emerge from the way the parts are connected and interact. Water molecules are not wet, but a collection of water molecules is wet. Neurons are not conscious, but a brain with billions of connected neurons is conscious. Individual ants are not intelligent, but an ant colony displays intelligent behavior, solving problems, making decisions, adapting to circumstances. The property emerges from the connections, from the organization, from the relationships between parts. And emergence is everywhere once you start looking for it. A flock of birds moving in coordinated patterns, murmuration, that's emergent behavior. No individual bird is planning the pattern, no bird is in charge. But through simple rules like staying close to neighbors and aligning your direction with theirs, the whole flock creates beautiful coordinated movement. A market economy, with prices fluctuating, resources being allocated, industries rising and falling, that's emergent behavior arising from countless individual decisions by consumers and producers. No central planner needed. Traffic jams, they're emergent phenomena arising from the interactions of individual drivers, and they can appear and disappear without any obvious cause, just from the dynamics of traffic flow. The climate, weather patterns, ocean currents, all of these are emergent properties of the Earth system, arising from the interactions of atmosphere and ocean and land and sun. And life itself is emergent. No individual molecule is alive, but cells, which are collections of molecules organized in particular ways, are alive. They metabolize, they reproduce, they respond to their environment, they evolve. And multicellular organisms are another level of emergence, where individual cells that are themselves alive come together to create something more complex, more capable, with properties that individual cells don't have. And societies, communities of organisms, are yet another level of emergence. And in each case, what's key is connection. It's the way the parts are connected, the way they interact, the patterns of relationship and communication and influence that creates the emergent properties. Connection is not just a feature of systems. It's what allows systems to be more than just collections of parts. It's what creates the new, the novel, the complex. And this raises a deep question about the nature of reality itself, about what's fundamental. We tend to think that things are fundamental, that particles or fields or strings or whatever the most basic entities turn out to be, those are what's real, and everything else, all the complex structures and processes. Those are just arrangements of the fundamental things. But maybe that's backwards. Maybe relationships are more fundamental than things. Maybe connection is more basic than the entities being connected. There's a philosophical view called ontic structural realism that argues exactly this, that the world is fundamentally a structure of relationships, and things, objects, entities are just nodes in that structure, abstractions we use to talk about particularly stable or important patterns in the network of relations. This is speculative, of course, it's philosophy, not settled science, but it's a coherent way of thinking about reality that takes connection seriously as a fundamental feature, not just an incidental property. And in some interpretations of quantum mechanics, this relational view is not just philosophy, but physics. The relational interpretation developed by Carlo Rovelli and others says that quantum properties don't exist absolutely, but only relative to other systems, only in relation to interactions. An electron doesn't have a definite position or momentum in some absolute sense, but only relative to how it's measured, relative to what it interacts with. Reality in this view is not a collection of things with intrinsic properties, but a web of interactions, of relationships, where properties only exist in the context of those relationships. Everything is connected because connection, interaction, relation is all there is. Without it, there's no reality at all. Let's bring this back to the human scale, to the personal and the practical. What does it mean for you, living your life, to understand that everything is connected? One thing it means is that your actions matter more than you might think, because connection amplifies effects, because ripples spread, because causes have consequences that branch and grow. What you do affects other people, who affect other people, who affect other people, and the chain extends far beyond what you can see or predict. A kind word might change someone's day, might change their mood, might affect how they treat someone else, and that might prevent a conflict or start a friendship or save a life somewhere down the line. You'll never know, you'll never see all the consequences of your actions, but they're there, rippling out through the network of human connection. And it means that the distinction between self and other, between in, here, and out there, between me and the world, that's not as clear as it seems. You are not isolated, you are not separate. You are a node in countless networks, ecological and social and physical and informational. You are part of systems that are larger than you, that shape you even as you shape them. Your thoughts are influenced by the culture you're embedded in, by the language you speak, by the ideas you're exposed to, by the people you interact with. Your health is influenced by the air you breathe, the food you eat, the water you drink, all of which come from ecosystems and agricultural systems and water systems. Your well-being is influenced by the society you're part of, by economic and political structures, by technology, by history. You don't exist in isolation. You exist in context, in relationship, in connection. And this can be overwhelming if you dwell on it too much, if everything is connected to everything else, if every action has unpredictable ripples, if you're responsible in some sense for consequences you can't foresee or control. How can you function? How can you make decisions? How can you live without being paralyzed by the complexity and responsibility of it all? And I don't have a complete answer to that. I don't think anyone does. But I think part of the answer is to accept that you can't know or control everything, that you can't trace all the consequences, that you have to act based on local information and immediate concerns, even knowing that there are larger systems and longer-term effects. You do your best with what you know. You try to be kind and thoughtful and careful. You recognize your connections and responsibilities without being crushed by them. And maybe there's something liberating in it too, something beautiful. If you're connected to everything, then you're part of something vast and ancient and ongoing. You're not alone. You're not isolated. You're not disconnected from the universe. You're woven into it. You're part of the fabric. You're a thread in the tapestry. And that means that your life has meaning beyond just yourself, that you matter in ways large and small, that you contribute to the whole even if you never see the full pattern. The air you exhale will be breathed by someone else. The heat your body generates radiates into the world. The thoughts you think and the things you create enter the flow of culture and information. The atoms of your body will be recycled into other organisms, other processes, continuing the cycle. You are not separate from the world. You are the world, taking a particular form for a particular time, connected to everything that came before and everything that will come after. And there's a spiritual or mystical tradition in many cultures that recognizes this interconnection that sees the separation between self and world as an illusion. In Buddhism, there's the concept of interdependent origination, the idea that all phenomena arise in dependence on other phenomena, that nothing exists independently or in isolation. In Taoism, there's the concept of the Tao itself, the way, the underlying unity and flow that connects all things. In Hinduism, there's the concept of Brahman, the universal consciousness or reality that underlies and pervades everything, and Atman, the individual self, which is ultimately identical to Brahman. The realization that you are not separate from the universe, that you are the universe experiencing itself, that's not just philosophy or poetry. It's an insight that people throughout history have arrived at through meditation, through contemplation, through direct experience. And modern science, in its own way, through its own methods, is arriving at a similar insight. That separation is an illusion, that connection is the reality, that everything is part of a unified whole. But let's be careful not to oversimplify or romanticize this. Connection doesn't mean everything is harmonious or that there's some grand purpose or design. Nature is full of conflict, of predation, of competition, of systems that work against each other even as they're connected. Connection can spread harm as easily as benefit. A virus spreads through connection. Disease follows contact networks. Economic contagion spreads through financial connections. Misinformation spreads through social networks. Connection is neutral. It's a structure, a property. It doesn't inherently make things better or worse. What matters is the nature of the connection, what flows through it, how it's organized, how it's used. And there are scales and degrees of connection. Not everything is connected equally or directly. Some connections are strong, immediate, consequential. Others are weak, distant, negligible in practice. You're gravitationally connected to every other mass in the universe, but the gravitational pull of a distant galaxy on you is so infinitesimally small that it has no measurable effect on your life. You're causally connected to every past event, but most past events have no significant influence on your present. So when we say everything is connected, we need to be nuanced about what that means. It doesn't mean that everything affects everything else equally, or that all connections are important. It means that connection is pervasive, that it's the norm rather than the exception, that isolation is difficult or impossible to achieve, that the web of relationships and influences is vast and intricate, and there are emergent boundaries and semi-autonomous systems within the larger whole. You are connected to the universe, but you're also distinct from it in important ways. You have a boundary, your skin, that separates you from your environment, even while allowing exchange across that boundary. You have agency, the ability to make choices and act on them, even though your choices are influenced by countless factors outside yourself. You have identity, a sense of self, a coherent pattern that persists through time and change, even though you're made of parts that are constantly being replaced. These boundaries and identities and agencies are real and important, even if they're not absolute, even if they're permeable and context dependent. So the picture we end up with is something like this. The universe is a unified whole, a single system, but it's a system with structure, with patterns, with emergent levels of organization. It's not just a uniform soup where everything affects everything else equally. It's a hierarchy, or better yet, a heterarchy, a multi-level web of connections and quasi-independent subsystems where different levels have different properties and different degrees of autonomy. Particles connect to form atoms, atoms to form molecules, molecules to form cells, cells to form organisms, organisms to form ecosystems and societies. And all of these levels are real. All of them have their own dynamics and properties. All of them matter. The connections between levels are crucial, but so are the structures at each level. You can't understand an organism just by looking at its atoms. You need to understand cells and organs and systems. You can't understand a society just by looking at individuals. You need to understand institutions and cultures and economies. The whole is more than the sum of its parts because of the way the parts are connected and organized. And this brings us to complexity science, which is the study of systems with many interacting components that give rise to emergent properties and behaviors. Complexity science draws on network theory and chaos theory and information theory and dynamical systems and computer simulations and other tools to understand how connection creates complexity. And what's been discovered is that complex systems, despite their diversity, share certain common features. They tend to be sensitive to initial conditions, as we discussed with chaos. They tend to have phase transitions, sudden shifts from one state to another when conditions change. They tend to self-organize, developing structure and pattern without external control. They tend to be adaptive, changing their behavior in response to their environment. And they tend to be robust yet fragile, resistant to some kinds of perturbations but vulnerable to others. And understanding these features helps us understand and potentially manage or influence complex systems, whether they're ecosystems or economies or social networks or cities or immune systems. We can look for the hubs, the keystone species, the critical nodes that hold the system together. We can look for feedback loops, positive and negative, that amplify or dampen changes. We can look for tipping points where small changes can trigger large shifts. We can look for leverage points, places where small interventions can have large effects. This is systems thinking, looking at wholes rather than just parts, at relationships rather than just entities, at dynamics rather than just states. And systems thinking is increasingly important in a connected world because problems are increasingly systemic. Climate change isn't caused by any single source of emissions. It's the cumulative effect of billions of individual actions and decisions and systems. And solving it requires changing those systems, not just individual behaviors. Pandemics spread through global travel and trade networks, and managing them requires understanding and influencing those networks. Economic crises cascade through financial connections, and preventing them requires understanding systemic risk. Social problems like inequality or polarization emerge from complex interactions of economic and political and cultural factors, and addressing them requires systemic interventions. The more connected the world becomes, the more we need to think in terms of systems and networks and interconnections, not just isolated causes and effects. Let me tell you about something called the adjacent possible, a concept from complexity science that beautifully illustrates how connection enables innovation and evolution. The adjacent possible is the set of all things, all states, all configurations that are one step away from the current state that can be reached by making one change or one connection. Think of it like this. If you're in a room with several doors, the adjacent possible is all the rooms you can directly access by going through one of those doors. You can't jump to a distant room. You have to go through the doors one step at a time. But here's the interesting part. When you enter a new room that opens up new doors, new possibilities that weren't accessible before, the adjacent possible expands as you explore it. And this is how evolution works, how innovation works, how knowledge grows. Evolution can only create organisms that are one mutation, one small change away from existing organisms. But each new organism opens up new possibilities, new niches, new adaptations that weren't possible before. Innovation can only combine and recombine existing ideas and technologies in new ways. But each new invention opens up new combinations, new possibilities. The printing press enabled books. Books enabled widespread literacy. Literacy enabled scientific revolution. Scientific revolution enabled technologies we couldn't have imagined before books. Each step opens new doors, expands the adjacent possible. Knowledge grows by connecting existing ideas in new ways, by asking new questions, by exploring the spaces between disciplines. And connection is what enables this exploration, what opens the doors, what expands the possible. And there's something profound here about the nature of creativity and discovery. New ideas don't come from nowhere. They come from connecting existing ideas in new ways. Newton said he stood on the shoulders of giants, building on the work of those who came before. Every scientific discovery, every work of art, every innovation is a recombination of existing elements, a new connection in the space of possibilities. And the more diverse your knowledge, the more connections you can make, the more creative you can be. This is why interdisciplinary work is so fruitful, why talking to people from different fields can spark insights, why exposing yourself to diverse ideas and experiences makes you more creative. You're expanding your personal adjacent possible, increasing the connections you can make. And this applies at the societal level too. Cities, for all their problems, are engines of innovation precisely because they bring diverse people together, creating opportunities for unexpected connections. Ideas and information flow more freely in cities. People from different backgrounds and fields interact. Collisions of perspectives happen, and out of that comes creativity and innovation at rates far higher than in isolated communities. This is called the urban effect, and it's one reason why cities have been centers of culture and progress throughout history. Connection breeds creativity, but connection also creates vulnerability, and we need to think about that seriously. The more interconnected systems become, the more ways there are for problems to spread, for failures to cascade, for small issues to become large crises. This is systemic risk, and it's a feature of highly connected systems. The financial crisis of 2008 happened because banks and financial institutions were so interconnected that the failure of some caused the failure of others in a cascading collapse. The pandemic of 2020 spread so rapidly because of global travel connections. Cyber attacks can spread through computer networks, affecting millions of systems. Supply chain disruptions in one region can affect production globally. The more connected we are, the more we share both benefits and risks. And there's a trade-off here, a tension between efficiency and resilience. Highly connected, optimized systems are efficient. They minimize waste and redundancy, but they're also fragile, vulnerable to disruptions. Less connected systems with more redundancy are less efficient, but more resilient, better able to withstand shocks. Modern supply chains are optimized for efficiency, with just-in-time delivery and minimal inventory, but that means they're vulnerable to any disruption. A more resilient supply chain would have backup suppliers, stockpiles, alternative routes, but that's more expensive, less efficient. We face this trade-off constantly in designing systems and infrastructure and institutions, and there's no perfect answer. It depends on values and priorities and the specific context. And I think as we move forward, as the world becomes increasingly connected through technology and globalization and the acceleration of information flow, we need to develop wisdom about connection. We need to understand not just that everything is connected, but what kind of connections we want to foster and what kind we want to limit. We need to think about building systems that are robust to failures, that have redundancy and diversity and adaptability. We need to think about governance and coordination at scales beyond the nation state, because problems are global and connection is global. We need to think about the ethical dimensions of connection, about responsibility in a connected world, about how to balance local autonomy with global interdependence. And on a personal level, I think understanding connection changes how we see ourselves and our place in the world. It can make us more humble, recognizing that we're small parts of vast systems shaped by forces and histories larger than ourselves. But it can also make us feel more significant, recognizing that we're not isolated, that our actions matter, that we contribute to the whole. It can make us more compassionate, recognizing that everyone else is also a node in the network, also shaped by circumstances and connections, also struggling and hoping and trying to make sense of things. It can make us more mindful about our choices, more aware of consequences, more thoughtful about impacts. And it points toward a different kind of ethics, maybe one based not just on individual rights and responsibilities, but on relationships and care and systems. If you recognize that you're connected to other people, to other species, to ecosystems, to future generations, then you can't just ask, what's good for me? You have to ask, what's good for us, for the system, for the whole? And that's harder, more complicated, less clear, but also maybe more aligned with reality, with the actual structure of the world we live in. There's this idea in African philosophy, Ubuntu, usually translated as, I am because we are. Recognizing that individual identity and well-being are fundamentally dependent on community and relationship. In Western philosophy, there's a growing interest in relational ethics, in care ethics, in approaches that foreground connection and interdependence rather than individual autonomy. And in environmental philosophy, there's the concept of ecological thinking, seeing humans as embedded in and dependent on natural systems, not separate from or above nature. All of these perspectives take connection seriously, recognize it as fundamental, and try to build ethical and political frameworks that reflect that reality. And maybe this is where science and wisdom converge, maybe understanding how deeply everything is connected, not just believing it, but really understanding it, really feeling it, really seeing it in the data and the equations and the observations. Maybe that changes us. Maybe it makes us wiser, more careful, more humble, more compassionate. Maybe it helps us navigate the challenges we face, the crises of this century, climate and pandemics and inequality and technology and all the rest. Challenges that are fundamentally about connection, about how systems work, about how to live in a world where isolation is impossible and interdependence is the rule. So when you ask why everything is connected, the answer is, well, it's complicated, but it comes down to this. Connection is fundamental to the nature of reality. It's not something added on. It's not accidental or incidental. It's built into the fabric of space and time, into the laws of physics, into the structure of matter and energy and information, into the processes of life and mind and society. Causality connects events through time. Forces connect particles through space. Networks connect nodes through relationships. Information connects systems through communication. Evolution connects organisms through history. Everything we've discovered about the universe, from quantum mechanics to cosmology to ecology to neuroscience to network science, it all points toward the same conclusion, that reality is relational, that connection is pervasive, that the web is the true structure of existence, and the boundaries we see, the separations that seem obvious, you and me, this and that, us and them, human and nature, mind and world, those are real in some sense. They're useful distinctions. They help us navigate and understand, but they're not fundamental. They're patterns, they're abstractions, they're ways of carving up a continuous whole into discrete parts for practical purposes. The deeper reality is continuity, is flow, is connection. And recognizing that doesn't erase the distinctions or make everything the same or collapse all difference into unity. It just means seeing the distinctions for what they are, contextual, emergent, partial truths within a larger truth of interconnection. And I think that's what makes this topic so endlessly fascinating, so worthy of contemplation and study and wonder. Because it's not just an abstract fact about the universe, it's a truth that has implications for how we live, how we think, how we relate to each other and to the world. Understanding connection is understanding ourselves, because we are connection. We are patterns of relationships, we are nodes in networks, we are processes in systems. And the more we understand about connection, about networks and complexity and emergence and all the rest, the more we understand about what it means to be human, to be alive, to be conscious, to be part of this strange, beautiful, intricate cosmos. So maybe the answer to why everything is connected is simply because that's what reality is. Not a collection of separate things that sometimes interact, but a web of relationships where things are the patterns of connection, where separation is the illusion and interconnection is the truth. And maybe understanding that, really deeply understanding it, is one of the most important insights we can have, one of the most transformative realizations available to us, because it changes everything. It changes how we see the world, how we see ourselves, how we live, how we think about meaning and purpose and value. It's not just science, though it's grounded in science. It's not just philosophy, though it has profound philosophical implications. It's a way of seeing, a lens through which the universe reveals its true nature as a unified, interconnected, dynamic, creative, beautiful whole. And we're part of that whole. We're not observers standing outside looking in. We're participants, we're threads in the tapestry. We're notes in the symphony, we're waves in the ocean. And that's both humbling and empowering, both limiting and liberating, both a challenge and a gift.